everyone. Welcome to another episode of the Top Cyber Pro podcast. I'm your founder and CEO, Jim West, and we're here with a wonderful guest. All of my guests are always wonderful. They're top in their fields, level 99. They're experts, multi-domain experts, PhDs, double masters. We've had them all. And we have another PhD. We have Katanya Kuntz that is joining us today that's going to talk about, we're going to talk a lot about quantum. And I've had a few guests to talk about quantum, and it's important because we don't have enough discussions about this emerging technology that's going to completely disrupt every industry on the planet eventually. And it's going to be a game changer, possibly from a theoretical standpoint, the last game changer from a technology perspective. And we'll get more into that because she's got a wealth of knowledge and experience. She's going to give us a lot of perspectives and insights. But without further ado, Katanya, welcome to the Top Cyber Pro podcast.
Thank you so much for having me, Jim. I really appreciate it.
So let's dive right into it. I see your banner behind you, Cubo. Let's talk about what is the why and the mission, because there's something on your LinkedIn that I like that was like making quantum accessible. And I like that because, for a lot of people, they hear about it and people are quick to just nod their heads, but they really don't understand it. They have misconceptions or they might have read some misinformation somewhere. So their expectations or their perspectives of quantum might not be close to reality. So, but let's start with the first part of the question. What is the why of Cubo?
Wonderful question. And I get asked that question a lot. So, when you say a quantum computer, right? Most people, their eyes will go blank and not really understand what you said, or maybe they heard about it in the news, but they don't know what it means. And so my mission with Cubo Consulting is to break that barrier, to be a communicator and a translator of this very complex deep tech that is the next quantum revolution, which I can talk about more later, and basically being that link from the research industry side of quantum technologies and then into hopefully the public.
Awesome. And then when you talk about making quantum accessible, I get that, you do a lot of maybe consulting and a lot of work trying to get the perceptions or the misinformation corrected, which is kind of the foundation. You got to start with everybody understanding what they're dealing with and correcting maybe some perception issues. But what would you say is like if you we hear a lot about like entanglement, superposition, a state is another thing we hear a lot about. What would be like if you had to say, hey, Cubo's number one from a consulting thing is we're targeting these properties of quantum physics as well as leveraging, these technologies in regards to these industries. If I mean, I know obviously you probably consult to anyone in any industry, but what would be the
Mhm.
primary focuses like right now? Like when they would say in the military, what's your 50-meter targets for your business?
Great questions. So yeah, by making quantum accessible, we're allowing any industry to get engaged into the quantum technologies. There are a few problems that are solvable right now with the quantum computers that are available currently to be accessed through the cloud. For example, logistics problems. So there's a lot of different industries that have those types of problems. And actually, QUBO is an acronym. It's quadratic unconstrained binary optimization.
Oh,
So
neat.
yeah, so it's also it kind of sounds like qubit, QUBO, it's kind of a funny.
Very
So it
clever.
works on multiple ways. And so a QUBO problem is actually not a quantum thing. It's a classical optimization problem. But that class of problem is very is runs very well on the quantum platforms we have right now. And so even though we're in what's called the era of noisy qubits, so
Mhm.
a qubit is a quantum bit. So in a quantum computer, we use quantum bits to do the computing. Um, and so because we don't have a lot of qubits that are stable and they're not stable for long periods of time, you can still solve problems, but they're just more limited right now. But as the technology develops, it opens more and more doors.
Now you mentioned noise, and so for those that are listening right now, like what are you talking about noise? Like the music's too loud? With quantum, it's very I'll use the word delicate, but we're talking like pecoseconds, nanoseconds of where you can get any use of these bits, if you will. And in that process, it could be a door slamming in the parking lot. This is why there's usually a lot of insulation. These environments are I think, near Kelvin or absolute zero for some of the applications of a quantum processor. But then you have like quantum as a service, which is like Bracket from Amazon, and then IBM will potentially and other providers will potentially have a quantum as a service. But you mentioned noise, so let's kind of delve into that because that is also related as well, kind of with error correction. We hear a lot about the error correction issues where they're trying to get, like you said, the consistency, the stability, so that you can use them for a longer run of a routine, if you will, and other purposes. Could you maybe delve into that a little bit more?
Yeah, and you're right. When I say noise, I do mean acoustic noise, sound vibrations, but also mechanical, and also electrical, and radio waves, and so electronic noise. So there's, as you said, quantum bits are very, very sensitive, and in some cases we have to supercool them to ultra cold temperatures, like close to absolute zero. So I mean, zero is the complete absolute no matter, no energy, nothing, right? And so that doesn't actually exist. Even the vacuum has a temperature, but we're
Mhm.
actually going colder than the temperature of the vacuum of space. Um, and why we do that is because certain properties become available when we start to go into those regimes. So, for example, superconducting. And so, one of the things you mentioned is superconducting circuits. And so, IBM, Microsoft, there's lots of different platforms that they already had the chip technology to create microchips, and they were making the chips smaller and smaller and smaller. But then, as you got into the quantum regime, where you're crossing from classical physics now into the quantum world, um, the circuits just don't act the same. You start to have weird effects like quantum tunneling. Quantum tunneling is as if a person could just walk through my wall right now, right? Like that's that in the classical world, that'd be the equivalent, right? And so, but we can use quantum tunneling where particles can go through a potential barrier that's like should stop them, but it doesn't. They can still get through. But we can use that now to do quantum computing with qubits and these superconducting circuits. And so you actually want the supercooled properties and yes, it gets very, very fun. And entanglement is another one, but you
Yeah.
don't have to have entanglement to make a qubit.
hmm Well,
Yeah.
a lot of folks are probably going, "What are you talking about? Passing through something?" So people may have does an obscure reference to quantum physics that I think came about in the 60s or 50s, and it was a property of when we think that we're touching a hand, we're never truly touching, and that's where quantum physics comes in. There are subatomic levels of physics where, yeah, it feels like my hand is pushing on the other hand, or that you could touch your face or touch a rock, touch a wall. But there's
Yeah.
always that space because when we think of like the classical science, videos and images of like an atom, right? You have like the proton and the electrons and so forth, the things
Yeah.
rotating around it. But there's space there, even in that rotation. There's space even with those electrons and protons and neutrons and so forth. There's that space means that you can never fully actually touch. So now when you get to that point, that when you get to that level, that atomic subatomic level, you have those spaces. And so
Mm.
when she talks about things passing through, it's passing through those spaces that we can't perceive, like with our eyes, and because we feel like, hey, my hand can't push through. We got Newton's laws of thermodynamics and laws of matter at play here. But when you get into quantum physics, it's a whole different ball game. And so that old adage of that where we're never really touching anything, yeah, we can't pass through it. But when you get down to that level, there's certain conditions and interesting properties that can happen. You started to
Did-
mention entanglement, so let's go ahead and just kind of give the viewers a quick, 101 on superposition and entanglement and any other properties of quantum physics that we're trying to leverage for this new emerging tech.
Yeah. Well, just finish what you were saying about the size of an atom and how much space there is. If you actually take like a hydrogen atom and
hmm
you blow it up to the size of a football field, like an American football field, the nucleus, the center, the atom, the proton that be at the center, it would be at the center of the football field, and the electron would be orbiting way outside where the bleachers are.
Yeah.
So, yeah, so there's lots of space.
Yes.
But I actually have some slides about
Yeah.
superposition and things like that. So if you want, we could wait and talk.
Actually, let
Maybe you
me,
want to do that.
I will make you host right now, and you can share whatever content you'd like to share. You are now
Okay,
the host.
perfect. Awesome. Thank you. Okay, so now I will share my screen and this one. Okay, share. Okay, and I'll just go full screen. How does that look for you?
Oh, it looks beautiful. Let's go. Let's go. Quantum
All
communication
right.
101. I love it.
Well, I had to give some kind of a title. So, as we've been talking, there's this second quantum revolution. And what does that mean, right? Like, wait, where was the first quantum revolution, right? So, the internet, computers that we're using right now, cell phones, all of these devices, the modern electronics that run your life, basically, those are all thanks to the first quantum revolution. A laser, right? This is
Yeah.
all based on quantum physics principles. But you're not actually using individual particles like atoms or particles of light called photons to do the sensing, the computing. That's the second quantum revolution, right? So the first quantum revolution brought us the laser, brought us satellites, GPS, things like this. GPS is actually a quantum clock, which is I can
Mhm.
go on forever. Anyways, so that's the second quantum revolution. And you mentioned myths, right? And so I want to
Yes.
knock this one out of the park right now. So there is a huge myth that AI is quantum. It is not quantum. It is not a quantum technology. AI, artificial intelligence, is a collection of classical, traditional computers that are working together, like the computer I have right now and a billion more that are very, very, very powerful, right? Which is why there's data centers going up all over the place
Yes.
to make that power, right? And again, the information is classically stored in a bit, and it's an on-off switch. You know, in your circuits, it's a transistor, and it can only have an on or an off position.
Mhm.
If it was halfway in between, that would break the circuit, right?
Mhm.
So that doesn't happen. So it's on or off. Now, what about quantum computers, right? So now
Schroeder's
quantum
cat.
Exactly, exactly. This is why I was like, oh, as soon as you ask me about superposition, I have to show Schrodinger's cat. So now with a quantum bit, a qubit, it can have a superposition or a combination state, right? And so superposition sounds scary. Combination, we all know what a combination is, right? And it's very complicated why it can have that property, but it can. That's just one of the principles of quantum physics.
Mhm.
And so Erwin Schrödinger, back in the 1930s, came up with a thought experiment, and some of you might have heard of this before, Schrödinger's cat.
Mhm.
And so this picture here, right? You see a cat that's in a superposition state of both dead and alive. You have a vial of poison that's in a superposition state of being either broken or not broken, right? And then you have this radioactive decay mechanism going on. And because over time, the probability of that vial becoming broken because the string collapses from the radioactive decay, blah, 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 right? So as time goes on, there's a higher probability that the cat is dead instead of alive. But we
Mhm.
won't know for sure until you open the box. And so this is like a macro or big example, right? Macro state example of a quantum principle, which is insane, right? We know we don't have zombie cats. They're
Yeah.
either dead or alive. But in quantum, this exists.
Mhm. And just to kind of add to that, there are interesting phenomena about states, which I'm sure you probably have a slide, but I wanted to, because of the Schrodinger's cat, there's an interesting phenomenon about like the double slit experiments and so forth, if you're watching it or not watching it. So there's some really unique and unusual phenomenon that occurs at these levels. But the one thing I wanted to add to is another a statement as one of the chief scientists at the National Security Agency said years ago when he's trying to explain superposition. The way he explained it, and this is the way I always explain it to folks, and it's still confusing, but the superposition is that it can the lights are on and off at the same time. And so,
Mhm.
with lights on, that's the one. If the lights are off, it's a zero. But with superposition, the lights can be on and off at the same time. And it's still hard to wrap our three-dimensional 2D 3D minds around into this new dimension of science, or where we're grasping and harnessing of science. So but yeah, that was what he had said. So sorry to interrupt, but I wanted to add that statement because it's again one of those weird phenomenons that we can't quite wrap our brains around because we're used to things. The lights are on or off, but when there are two conditions at once, it kind of throws a monkey wrench into our perceptions. But it is purely still based on laws of nature. And that's the thing. I always tell people when you get to harness the power of the atom, we've seen what we've done when we split the atom or had the fusion of the atom. We've created great destruction, also tremendous amount of energy and power. And so when people
Mhm.
think about, oh, well, how much more compute speed are we going to get when we start using superposition? I'm like, well, remember what weapons and bombs were before the atomic weapons were made. And they were like, oh yeah,
Mhm.
it was like a huge exponential jump in like the TNT measures that they had to do were just off the scales when he started getting into nuclear and atomic level weapons. And so again, harnessing the power of nature, there's nothing on the planet that we can make that can compare to the power of nature. And this is another great example of it. So sorry to go off on that tangent there,
No,
Katanya.
that's
Please
not a
continue.
tangent. No, that's not a tangent. And what you're saying is exactly correct. We are literally using nature to simulate nature. So
Yeah.
a quantum computer is using nature, using the fundamental particles of nature to do a calculation, to simulate a model, right? And so when we're using classical computers, we're actually using like a digital it's not it doesn't have all the same properties as a quantum system, and so it's like an approximation. And so we can't solve certain problems because they're literally impossible. You would need
Hmm.
quantum compute or supercomputers to calculate for decades or billions of years or something ridiculous, right? But with a quantum computer, it could be solved in minutes,
Hmm.
like simulating new biological materials, like chemical materials, new medicines. These are very complicated calculations to do that we use supercomputers right now. But if you use a quantum system to simulate that, it could be solved quite
Hmm.
faster. And you can also, because it's in the superposition state, these qubits allow you to explore a computational space that is just not possible with a classical computer. And so I have an analogy for that. It's an analogy, so it's not
Okay.
scientifically correct, right? So think of a classical computer when it's solving problems, it's like it's locked on a 2D plane, like a piece of paper, right? So it can go up and back and forth and side to side, but it can't go up and down. Whereas a quantum bit, it's like it has this access to an additional dimension, right?
Hmm.
And so now it can access that third dimension and it can go up. And so you can think of a basketball. And so a quantum bit can explore that whole surface of a basketball, right?
Hmm.
Whereas a classical bit would be stuck at the poles. It's either the top or the bottom. It
Hmm.
can't. So because the qubit can have all these additional properties and values, we can then do these calculations that are impossible with a classical computer.
Another way
And
that
some
I explain
examples.
that to folks
Yeah.
about the computing power, I have a animated GIF that I use in a presentation that I give at conferences, and the
Oh
one
yeah.
shows the single threaded type of traditional classic computing where it's trying to figure out a maze. So it tries a path, it's not successful, starts again, and keeps trying paths one at a time because that's the whole
Yeah.
thing about the what's the word I'm looking for? Single threaded processing, but it's basically, there's no true multitasking. You can have multi-processors, multi-threads in classic computings, but they're just trying their own different pathways. Whereas with a quantum computer, it tries all the pathways at once because, like you said, that basketball, it has every single possible dimension to explore. And so therefore the animation I have shows the single threaded trying each path one
Mhm.
at a time till it's successful. And then when I click the clicker to the next screen, it's like it's solved instantly. And that's kind of the visual that I give people on the compute potential power that we're dealing with.
That's amazing. That's exactly the type of graphic I want to make for my own website to explain how a quantum computer tries, all possibilities at once.
Yeah, I'll share those gifts with you after this podcast.
Excellent, excellent. Well done. And so some of the platforms, like we said, superconducting circuits is one, right? Other ones, you can use the spin of an electron.
Hmm.
So quantum spin is just a property of an electron, like how an electron has an electric charge, negative charge. It has a mass, right? And so it also has another property called spin. And it's either spin up or spin down. And so it's in a superposition state until you measure it. And so that's a qubit. Yeah. And then we have obviously particles of light and photons. Um, but yeah, because of these special properties, a quantum computer can potentially solve problems that are not possible with classical computers, could have a lot more power, and just operate more efficiently. Yeah.
Awesome.
So, oh yeah, I got one more. So
Okay.
lots of people think that this is the quantum computer, right?
Hmm.
They see this huge chandelier, gold plates on
Hmm.
various levels. There's brass and things, and it's about the size of half of a human, right? But actually, this is just the fridge
The
to
fridge,
make
yeah.
the device work in one type of quantum computer.
And there it
So
is.
this is a D-wave
Hmm.
circuit. So they do superconducting circuits. It's a different type of quantum computer. Instead of qubits, they're doing an analog version. And so it's called quantum annealing. And so this is also very powerful for optimization problems. And they have demonstrated quite a few real life optimization problems. And they help corporations currently to for the traveling salesman problem, for example, like that's for deliveries and things like that. There's a few companies that work with D-Wave to optimize that. And so this little tiny chip in the middle there, that goes down way at the bottom because each of these levels is actually bringing the temperature down. And
Hmm.
so at the very, very bottom here, it's around 1 Kelvin or less. And so 1 Kelvin is just 1 degree above zero. Yeah. Oh yeah, and then I wanted to also mention that there's companies that make these cryogenic fridges.
Hmm.
For example, Zero Point Cryogenics in Edmonton, Alberta, in Canada. And these fridges are not just for quantum computers. It's also for other quantum systems like quantum memories, quantum sensors, detectors. So this is kind of one of the major workhorses of the quantum industry right now. And you can see these two gentlemen working on the system.
Hmm.
And it's important to point out that you do not need a PhD in quantum to get
Yep.
engaged in the industry because the founder of Zero Point Cryogenics has also given an analogy in a gold rush, right? Everyone needs a shovel. And we're currently
Mhm.
having the quantum gold rush, and everybody needs a cryogenic fridge, most people.
Yes.
Yeah.
And that brings me to a great question. We hear a lot of discussion about different startups and other companies that are taking different approaches to the temperature issue, right? Because the
Mhm.
most common question the average person says is when I'm going to have a quantum computer sitting on my desk. And I tell people unless someone can get a quantum or a system that connects into a quantum circuit or platform probably is more ideal. But an actual quantum computer on your desk anytime would, I like to, people want to hear times, right? And I hate to get
Yeah.
into that because we're doing assumptions and guesswork. But to me, what do you feel about a lot of different approaches when people are trying to achieve, having qubits operate at near room temperature or at room temperature? What are your thoughts on that and your insights on that?
Yeah, well, it's important to point out that there's other platforms that don't require cryogenics to operate. And so there's room temperature devices. So they might need a little bit of cooling, but maybe it's only to like minus 30 degrees. And so you
Hmm.
can easily achieve that without cryogenics. There's also platforms that use light. So photons are individual particles of light. They can also have a superposition state of 0 and 1, and you pick one of their properties to be that. So it could be polarization, right? So if you have polarized sunglasses and you're looking at your phone and you rotate them, 90 degrees, you'll see the screen goes dark, right? And that's because the polarization, your screen is giving off a certain light at a certain, sorry, is giving off light at a certain polarization.
Hmm.
And your glasses, then when you rotate, if it's rotated, exactly opposite, if your screen is giving off horizontally polarized light and now your polarizer is set to vertical, you're only going to let through vertically polarized light, so it goes black, right? There's actually a cool demonstration I do with school kids where they're all holding big polarizers, right?
Uh-huh.
So one person's holding a polarizer, and then two other people have other big sheets of just polarization film. And you can make the person that's holding it disappear because you
Hmm.
can rotate the polarizers and then you can bring them back, So it's kind of
Neat.
a cool demo. Yeah, so you can use polarization, for example, to encode qubits. And so you don't need you can operate those types of devices, detectors without cryogenics.
Hmm.
Yeah. So when would you have a desktop quantum computer? Well, first off, do you need one? Like these are So the future looks to be hybrid, right? So it sounds like it's going to be a pain in the butt to try to make, for example, an Excel spreadsheet on your quantum computer. So you're probably going to have lots of uses for the technologies right now. And there's a lot of merging of AI with quantum. And so AI can help with optimization problems as well. And then when the problem gets to the point where it's too hard for the classical algorithm, you outsource that part to your quantum computer. And so it's probably more of a collection of clouds, like quantum clouds and the quantum internet. And I can explain the quantum internet later. I've got a little technical bit coming up.
Okay.
But if you want, I can stop sharing my screen because I
Oh,
think
if
that
you
was.
have more content, I'm here for it.
Oh,
So,
okay. So we can just keep it up. All right, cool. Yeah. So, and so whether you need a quantum computer as if it like a quantum cell phone, right? If anything, the public would be more interested in the encryption benefits of quantum technologies. And so, I wear two hats, right? I have my role with quantum consulting, and then or sorry, with Hubo Consulting, but I also have my research academic role with the University of Waterloo at the Institute for Quantum Computing. And so with that, I'm working on the KeySat mission. So that's the quantum encryption and science satellite. And so this is Canada's first quantum communication satellite. And it'll be launching in roughly a year, so late 2026. And why do we care about this? Well, a quantum computer can potentially make some of our public key encryptions vulnerable. So when you're doing online banking, when you're doing online shopping, anything like that, you are using a type of, oh,
oh yeah, I'm gonna go ahead and put us full screen. So sorry to interrupt.
that's okay. I didn't have all of that set up. Now I'll have it set up. There we go. Anyways, and so if your current encryption could be vulnerable to a quantum hack, right? We want quantum encryption to be able to take over. And so there's already other, and I know you've probably talked about this, like post-quantum cryptography
Hmm.
and the NIST algorithms, and so those are harder math problems to try to prevent a quantum attack, but they're not necessarily fundamentally secure. So whereas one-time pad encryption, right, where that's a classical encryption method, it is 100% theoretically secure if it's implemented correctly. And it's so now it's a matter of how do we get a key share between two parties that would be quantum secure, right? And so if we use particles of light like photons, and now all of a sudden, if my eavesdropper is trying to intercept the light that I'm using to transmit the key, to generate this key, um, that eavesdropper is going to have to measure the light. I'll have to do something with the light, and I will be able to detect that in my measurements and when I'm monitoring the channel and things like this.
Hmm.
And so fundamentally, in quantum physics, measurement disturbs the state. And when you talk
Hmm.
about state, in this case, we're talking about the
Because
qubit.
once you look at it, it
Yeah.
changes. And so, yeah.
And same with what you were saying before, Young's double slit experiment. I actually created an educational demo for my company that demonstrates that the observer making a difference. So without the observer there in the double slit experiment, you see the interference fringes because the light is interfering, because the
Hmm.
light doesn't know, did I go through the left slit or the right slit? But if you put an observer there, if you put some sort of marker that now flags the light, oh, I went left, oh, I went right. Now there's distinguishing, and that
Hmm.
distinguishing information, once it exists, quantum knows, right?
Yeah.
Once the information exists, the behavior changes, right? And now the interference fringes are gone, and you just see one spot of light on the
Hmm.
screen.
Yeah. So again, from a post-quantum cryptography perspective, as well as quantum key distribution, quantum random number generators, those are kind of what I call
Mm,
the current solid use cases for properties of quantum right today. And so when people
mhm,
talk about other applications yet, this is the thing. If entanglement gets involved into like telecommunications, it's gonna be all over the news. It's gonna be whatever that company is gonna become for that quarter the most profitable company on the planet when
mhm.
they're the first to market. So what I tell people is, take things with a grain of salt. When you see these big news stories, earlier this year, the big one was when Google Willow AI did their announcement, put out their stats and numbers, and it was like people were going crazy, like, oh, it's did it in so many septillion years and did it in 5 minutes. But people just, most people like with the news, they read the headline, they might read a couple bullets in the story, but they don't read the actual research, the documents, the white papers, etc., the journals that they publish out to the community. And this is very key. When China says we broke AES encryption, you got to read the documentation. You got to read what methods did they do? What was the actual bit stream? And once people started digging through the story, the headline, they're like, oh, it
Mhm,
was only 22-bit. But the thing is there's still validity in some of these stories, meaning maybe it wasn't 250 AES 256 or AES
mhm,
512, but the idea
mhm,
that they have an approach that can weaken the encryption standard and algorithm, that's still a concern. Weakening an encryption, as you know, when I explain to people, there's really two things that come. The bottom line up front for encryption is time and randomness. The other word that's preferred is entropy. And so entropy has a lot to do with the Newton's second law of thermodynamics. There's a lot there when you want to look up heat decay of the universe. If you want to go down a dark rabbit hole of the internet, folks, heat decay of the universe deals with that. But it's scary. I'll just explain it real quickly. The idea is that at any moment, once there's a heat decay in the universe, it's just the lights go off instantly. We won't know when. It'll just be blink and it doesn't exist anymore. That's terrifying to think about in one aspect. But anyhow, back to the point of encryption. When you hear about, these days about septillions of years in 5 minutes, it's talking about bridging that gap of time. And in cybersecurity, we talk about brute force, right? Brute force is you try every possible combination till you guess it right. So with brute force comes to this exponential computer power from quantum that's going to give us in the coming years. The concern is now can it bridge that time? Just like when Google Willow put that story out, everyone's like, it did a routine that would have taken a supercomputer 6 septillion years. It did it in 5 minutes. That raises a lot of eyebrows because one, it does demonstrate the exponential off the charts compute that it has, the capability. But at the same
mhm,
time, people didn't read because they immediately thought, does this mean it could break AES 256? It could break all of our encryption standards. No, you have to read what was the routine it was running, what was the problem it was trying to solve, and so that's important when we have these discussions, right? Then, of
mhm,
course, a few
mhm,
months later, Microsoft had their chip announcement and a lot of stuff. But yet, Microsoft, I'll give it to them, they're more focused in their press releases about error correction. Like, so you'll have
mhm,
different initiatives and strategies to how they're trying to solve different problems. Google AI didn't have a lot about error correction. They were more focused on the compute. Microsoft was more focused on error correction, and then you got Amazon with their approaches where they're trying to harness through a partnership with QEra, they're trying to harness more natural properties of the atom, which, as we said earlier, the more closer you get to the nature of it, the
mhm,
faster that if you can harness that, that's the fastest that's theoretically possible. But back to the point of
mhm,
encryption, you have the time and you have the entropy. And so when we talk about post-quantum cryptography, these new algorithms, people try to wrap their heads around a math problem. But imagine math, in our simple minds, we think 1 + 1 = 2. And that's
mhm.
simple linear algebra basically, but a linear equation, 1 + 1 is this. But with these algorithms for encryption standards, you see these names like, RSA is three guys' names that have mathematicians that are really smart mathematicians on the planet that get together to come up with these complex algorithms. Because what's the weird thing about math is we think it's absolute, but it's not always absolute when it comes to encryption standards. So what they do is it produces what appears to be randomness, but the thing with
Mhm,
randomness is not always so random because it's a certain routine, there's certain steps it goes through. So with the current CNSA suite of algorithms, which is the National Institute for Standards, they have approved certain algorithms that were good until now we have quantum coming. So now this new term from this is
mhm,
called post-quantum cryptography. And there's been a
mhm,
new round of mathematicians and teams competing to pass the NIST bar, if you will, to be
mhm,
accepted as the PQC. Now, there's a term, folks, that you need to be very careful with that you won't see the agency or NIST or anyone say. They're not going to use the term quantum proof. They got away from that a few years ago because they used the word quantum resistant. And when you think of a fire in your house, do you want to be fire resistant or fireproof. Well, everybody wants to be fireproof. The issue is we still have to deal with science. And in science, we have the whole idea of you have to put out a hypothesis and it has to be tested. And because we don't have quantum computers that have been purposely built and to serve a routine to run like a Grover's iteration to tackle an encryption standard yet. None of them, I'm sure they're doing this in the background and we just don't got public news of it. But bottom line is that until any of the PQC algorithms get broken, we still have that assurance that there's a high enough entropy, which is that randomness. And what used to be the property of having randomness was called key space. So, like for example, an AES-256 pair has so many potential combinations, and the math is like I think 60 something characters long. It's a very
Mhm.
long number of possible combinations for a single session with
Mhm.
AES-256. So, with that being said, the math for classical computers, there's not enough time and not enough materials on the planet to make that many classical computers to even begin to take that time and shorten it down. So we have a lot of assurances on the time side of things with that level of entropy. But with quantum's
Mhm.
off the chart exponential computing power, it's going to really tackle that time issue. It's going to really drop that time. So when you read these reports like Google Willow AI, it did a routine in 5 minutes that takes a supercomputer 6 septillion years. It is a big deal because it demonstrates the compute power, the raw compute power. But please, folks, don't just jump out your chair and say we're all doomed. With any news story, read the sources, read the science papers, dig 2 or 3 levels deeper to get to the real information. And that's what I caution. A lot of these press releases are really to, invigorate stakeholder support, to drum up funding for the next series or round of experiments that they're doing. So they are doing this they're still a company. They still have to get support from a board and stakeholders. So take everything with a grain of salt, folks. It is exciting that we have what I see as the beginning of a quantum chip war. But like I said, I think that we got to make sure with misinformation, making sure we keep people's perspectives rooted in reality is very key moving forward. So I know
Mhm.
I went off on a long tangent there, Katanya. But with that being said, one of the things I did want to talk to you about, I know we could talk forever about the technology because you have so much knowledge and experience, but I do want to respect your time. You also do a lot of training. I think you mentioned to me when we were coordinating this podcast that you just delivered a hugely successful training, and I think you're partnered with an institute that delivers this training. Could you talk a little bit more about that training?
Yeah, for sure. But I also wanted to add that you're right. There's entropy for a service, and so there's a lot of companies now that are offering randomness as part of a quantum service. So
Yes.
just a side note.
Yeah.
Yeah, so Cubo is very proud to be partnered with NATE, the Northern Alberta Institute of Technology.
Okay.
They're a post-secondary institute in Canada. And I've been delivering online live courses. And so there's 2 quantum certificates, and these are the first, definitely in Canada, possibly globally, that are targeted to specific groups, and it's short courses. And so for the engineers side, it's 4 2-hour courses,
Okay.
and for the executive side, it's 4 1-hour courses.
Okay. Well,
Yeah,
hey,
and I have a
you're
I have
talking,
slides for everyone.
very digestible times pieces. Not, you don't have to take a whole week off, and you can
No.
ingest it piece by piece. Folks, before you start, trying to Google and look up Nate, I will have all these links. So Cubo's link, Nate's link, and everything that we've discussed, and more, because I'm sure Katanya's just going to give me a whole list of useful URLs with more information and knowledge on quantum computing. So they will all be in the description below. So I'm going to save you that Google search. But with the training, could you maybe talk a little bit more about it? Like what can someone, like if I was signed up, let's start with the engineers, right? What would be
Yeah.
some of the things that I would learn like day one? Like the first session I'm gonna like have, what are some things you could like knowledge nuggets you could drop on me?
Yeah, for sure. So I could share my screen again if
Oh
you want
yes,
because
I'm sorry. Let's
I do have some
get you back
slides
here.
about it.
1 second.
Okay, cool. Right. So we left off there. So I did prepare a
Oh
little
yes.
short sample, but we can go straight to the courses and then we can go back to this. But
Okay.
Um, yes. So, like I said, Cubo has partnered with Nate to offer these 2 quantum certificates. The next cohort is coming up in November, but there'll be more courses announced in 2026 as well. And so For the executives course, there's, like I said, 4 1-hour courses. And so
Hmm.
you start with quantum solutions for executives. So basically in that course, I give you an overview of like what you were saying earlier. You hear in the news all these announcements from different quantum companies about various things, and like what's hype, what's real, what's actually happening, what could I get engaged in if I want to as a business. And so that's what I'm trying to target with all of this training. It's
Hmm.
targeted, it's very short for that reason. And it gets you engaged into the quantum industry. So the first one is an overview of quantum technologies, because there's not just computing, there's also quantum sensing and
Hmm.
communication. And then the following three get more targeted into the industry. So for the quantum computing use cases, I'll actually step through business use cases of like real results where a company engaged a quantum computing system and we're able to find real results from solving optimization problems, improving. So maybe you're an insurance company and optimizing premiums is a very complicated and lucrative area. So quantum could help with that. And then the data security and quantum communication. Again, these are all non-technical, so I would not go into what is quantum key distribution and that kind of thing, but I would talk about what is the quantum threat. Why could a quantum computer potentially hack your current encryption? What
Hmm.
is PQC? What's the difference between that and a quantum solution? Why is it not called quantum proof? Like all the things that you were mentioning.
And I love
Um,
this last one in particular because if you're a manager or executive, there's not an I have not seen any strong training for the sensing use cases because we all hear about
mm,
entanglement and superposition if you're somewhat in the know of quantum, but not enough
mhm,
people are talking about the sensing use cases. So I love that
mhm.
that you have this covered here.
Yeah, and it's actually one of the more mature quantum technologies. There are
Yeah.
quantum sensors that are being deployed or are deployed currently for various locations. So, in the oil and gas industry and mining and things like this, there's actually a company in Canada called SB Quantum, and they make devices to help with improving your maps. So it's going to improve the magnetic map field. So it's using an atom. Well, actually, it's using a nitrogen vacancy center inside diamond to very, very carefully map the magnetic field at a location. So, and you can get details that you can't currently get with our classical systems.
Yeah.
Also,
And folks,
GPS.
when she mentions the diamond, this is
Yes.
very, very, very important. These are absolute perfect diamonds to operate in. So when we think of typical diamonds with their flaws and imperfections, it has to be near perfect diamonds. And that's a very, interesting thing to understand how many near perfect diamonds are even made or found. Uh,
Mm.
Quick question on that though, could they use a manufactured diamond?
Well, I believe to get the best results, you want to grow your NV center yourself. And so there might be some raw material they start with, but then a lot of it is like nanolithography and in a clean room yeah.
Yeah.
So you actually create it yourself so that because you want to purposely dope certain materials into it because you want a
Boron being
nitrogen.
one of them. Yeah.
Yeah, exactly. And so nitrogen vacancy, meaning that there's a nitrogen atom that's taken the place of one of the carbon atoms, and then a vacancy, meaning there's literally a vacant spot adjacent to it. And
Mhm.
so that pair of nothing plus a nitrogen atom creates a qubit
Mhm.
that you can control. Yeah. Yeah.
Science, folks, science.
And I do get into the engineering side
Okay.
for I do have a sensing so yeah, so for now for the engineering certificates it's more technical courses and they're obviously 2 hours because of that. The first course again, it's an intro to the overall area, the industry, what is uh, again, I'm assuming no technical knowledge on the quantum side, right?
Yeah.
So you're the type of audience would be like an RF engineer, electrical engineer, mechanical engineer, and all of a sudden you want to know what is quantum.
Yep.
And then I go into the quantum platforms, so the computing platforms, the sensing platforms, and then the communication platforms. So real technical details, but not too far, right? And that's why the Q&A, it's live. So if you have technical questions, I'm happy to answer them. And we had some really great discussion in our pilot session in May. The students were blown away by the content, so I'm very excited to see what the next cohort thinks. Yeah.
Awesome. And folks, there's a QR code obviously there. There's websites. We'll have the links as well in the description. But this is just phenomenal to see that these are what I call bite-sized chunks. You're not getting overwhelmed all at once, and the fact that you have a live person that's going to answer your questions. I mean, what better? What more could you ask for? And I believe that the courses are super affordable. I think when I checked them out earlier, one's about $400 or $500. Other one's about 250 to 300. It's not going to
Yeah,
break the
Canadian.
bank. Yeah. Which it should, because obviously
Yeah.
in the future, as more content gets added, those future courses probably. But you know what? It's whoever adopts and learns this technology can obviously be more valuable in your position, your job market, etc. And so again,
Mhm.
it's all about training and upskilling. The key word that we've heard for like the past 6 years is that word upskilling. When it comes to AI, if you just don't want to, if you want to shun the technology, say I'm not going to learn that, you may find
Mhm.
yourself just like there was an announcement today. Salesforce is laying off 4,000 people because they're replacing them with AI. And whether or not that works out for Salesforce to be determined, but there will be some jobs taken over due to the increasing usage of, and reliance on technology. But this is what I tell
Mhm.
folks: you should always be learning, studying, growing your capability set, your knowledge base, and this is another opportunity to grow into something like I said is going to be probably the biggest disruptor in
Mhm.
technology that we have seen in a long, long time. Because again, this is hitting what I call the theoretical limits of science when it comes to speed. And so this is just going to be
Mhm.
phenomenal. I'm here for all of it. So yeah, we talked about Cuba. We talked about there's another company that I wanted to talk about, and it's called KeySat. It's QEYS Sat. And so, could you talk a little bit about their mission, what the work that you do with KeySat, and an interesting name. It stands for something.
Yeah, definitely. Yeah. So, but KeySat isn't a company, it's the mission name
Mission name.
for the
Okay,
satellite
my
mission. Yeah,
correction.
yeah.
Yeah.
Yeah, no worries, no worries. So that's what I do with my university job. So I work with the Canadian Space Agency. They own and operate
Wow.
this this satellite, and Honeywell is the technology developer, and so they are building the payload. And like I said, we were going to launch. So KeySat stands for the Quantum Encryption and Science Satellite, and we're going to be launching in roughly a year, so late 2026.
Mark your calendars, folks. That's going to be a big launch coming up
Yeah.
next year. So
And why do we want to do that?
yeah.
Well, quantum information is very, very delicate, right? We've talked about how noise can disrupt qubits.
Hmm.
Noise, literally, like if you had a quantum computer and then a truck drove by in front of your building, you would be able to measure potentially the vibrations caused
Hmm.
by that truck on
Yes.
your qubit noise, right? And so the other thing we have to consider is when we want to connect quantum computers, because think about how powerful your computer is right now if it wasn't connected to the internet, right? Versus when it
Okay.
is. And so with a quantum computer, standalone computers will be very powerful, but the best will be a network of quantum computers. And also, if you want to do a quantum key share and you want to securely communicate, right, with two parties, and you want to keep the integrity of those photons in transit, you can't just send them through our standard internet fiber optic cables, unfortunately. So because photons are sensitive, right? So if they're lost to the environment, that information is lost, right? And
Hmm.
when you have a quantum state, if you lose too much of your light, of your information, that quantum state is no longer quantum. It'll start become classical, or it'll
Hmm.
just you won't have a signal at all to detect, right? And you can't just crank up the power like what we
No.
do right now. We use amplifiers to send signals, 40,000 kilometers around the Earth. There's some fiber optic cables in the ocean. I
Mm-hmm.
have a map. I don't have that here, but in one of my presentations with Nate, I show a map showing a heat map of like all the lengths of fiber optic cables, and it's like that's not possible. We've got a 300, maybe 500 kilometer limit on how far we can send quantum information, photons,
Mm-hmm.
through fiber optic cable. And
So
because
that's
of
where
the
the
no
satellite
cloning,
comes in.
exactly, and because of the no cloning theorem, we can't use amplifiers to boost the
Mm-hmm.
signal if it
Because it's
gets lost.
interference.
Yeah, exactly. And so what we do instead is go to space. And so
Mm-hmm.
if you have a ground station with a telescope, right? Telescopes are really good at collecting light from stars.
Mm-hmm.
Well, it turns out you can also shoot a laser up there
Brilliant.
too. Yeah, and so KeySat is a quantum uplink mission. So our sources, our lasers will be on the ground, our quantum sources, and then the satellite will have the detectors. And so the satellite is the receiver.
Mm-hmm.
So the way we talk about, quantum key distribution, it's always A to B, Alice to Bob, right?
Mm-hmm.
A to B. And so Alice is the sender and Bob is the receiver. So the receiver is going to be up in space. And now, what if you're two people you want to connect, right? What if one is in Canada and one is in Australia? What are you going to do? You can't just go through fiber optic cable.
Yeah.
So what you do in this mission, what we're going to do is we have what's called trusted node quantum key distribution. So the satellite is first going to do a link with ground station 1 in Canada. And then it will go over its orbit, right? So it's giving me a LEO low Earth orbit
Lower.
satellite.
Yeah.
And then it will go over to the other ground station, do a link with that ground station. Now the satellite knows both of the keys that have been exchanged, right? So that's why it's called trusted node, QKD, right? So if the satellite was hacked, then that would be bad, and the hacker would learn the key, right? So this is a technology demonstration mission, right? And so the next stage would be to do untrusted node QKD, which is where entanglement can come in, right?
Mm-hmm.
And so that's where even if the satellite was hacked, it doesn't matter. They won't learn
Yep.
the key.
Yep.
But so first we'll do untrusted node, or yes,
Listen.
untrusted node QKD, and so once both ground stations have done their key exchange with the um, satellite can do an XOR, right? Operation, a multiplication, basically, of the two keys, announce that. And because of the pure randomness of the signals, because these were generated using random photons, random measurements, everything's quantum and random. And so there's no correlation. And so if once you do an XOR and you publicly announce that, it's just noise. It doesn't make any sense unless you have the other half,
Mm-hmm.
right? And so, for example, Ground Station 1 could now take that public announcement from the satellite, XOR it with their key, and get what Ground Station's 2 key is. And now they can do a secure message exchange using that key.
Excellent.
And you can do
This-
that over the classical channel. That doesn't have to be with quantum.
yeah.
Yeah.
So, one of the other things I wanted to talk about, so that's super exciting. So, definitely
Yes.
folks want to
And
follow her on LinkedIn, her socials, and as well as the Canadian Space Agency because that's an exciting experiment. I mean,
yeah.
wow, that's just to me that's super exciting, at least. So, what I like to do, Katanya, do you have any more visual content you wanted to show? Because I want to kind of talk, get into the other half of the podcast. Do you have any more content you can show us?
It's up to you. I mean, I do have some slides talking about
Well, I
quantum
also
key
want to keep in
distribution.
mind where we're approaching the hour, so I don't know if you have another call immediately after this, or if we have a little bit more time we can work with.
No, I'm good for another hour.
Okay. Well, if you have more content, by all means, if you want to share your content
It's kind of
again.
like a snapshot of the types of material that I present in the NATE courses, and so I thought it would be a
Oh yeah,
nice
I'd love to see it.
preview.
Let's
Okay.
let's see. I think if you share your screen again, it should
Yeah,
automatically
I'll do
pop up.
that. And share.
There we go.
Perfect. So, like I said, this would be material that I would present at a more high level for the executive course, but for the engineers course, this is the type of level I'm presenting. So we already talked about the quantum threat, right? That a quantum computer could potentially hack our current classical encryption. Things like Shor's algorithm is one of those algorithms that can be run on a quantum computer that could potentially hack
Hmm.
RSA encryption. However, keep in mind that quantum computers are not better at everything, right? There are some operations that are still hard to do with qubits as well as classical bits, and that's why post-quantum cryptography, or PQC, is a viable option and is currently being installed right now and to help mitigate these attacks because even AI attacks are becoming more and more frequent and
Hmm.
powerful, right? And so PQC should be able to mitigate that as well.
Yes.
But then what is the quantum solution, right? So quantum key distribution, or QKD, is the quantum solution for the encryption threat. And so QKD is the real-time generation, not distribution. The founders have actually said to me, I wish I called it quantum key establishment instead of quantum key distribution, because everyone
Yeah.
thinks that one person has the key and it's going to the other. No, you're generating it together in real time.
Hmm.
And so Alice and Bob, Alice the sender, Bob the receiver, they are going to generate this secret key using particles of light called single photons. And so once Alice and Bob have generated their shared key using their single photons, and they're sure that it wasn't tampered with by the eavesdropper because we can measure these signals and make sure that it was a secure key, then you can use that key in a one-time pad encryption. And
Hmm.
that is theoretically 100% secure method,
Yep.
right? And so the security of QKD, it's not based on solving harder math problems like factorizing large numbers like RSA or PQC with a more difficult mathematics, but this is based on physical processes that are not vulnerable to a quantum computer. And so I mentioned this earlier, like what is the quantum internet? Why would we need to have a global network to connect our quantum computers? Well, because quantum information is sensitive and we can't just turn up the power if we lose some of the light. And we
Hmm.
can't use, because then if we turn up the power, it becomes a classical signal. It's not quantum anymore. And if you use classical amplifiers to increase the distance, well, that isn't allowed because of the no cloning theorem. You're fundamentally like, in Star Trek,
Yeah.
when you use the teleporter, right? Well, it turns out when you're teleporting, you cannot make a clone, right? You
Yeah.
have to destroy the person in one location and recreate them in the other location. So you cannot make a perfect copy, which is a good thing because that's part of the security,
The
right? That
uniqueness
means an
of nature,
eavesdropper.
right?
Yeah, yeah, yeah. So an eavesdropper can't just steal a photon, make a perfect copy of it, and then give it back to you. So that's part of our security. But it also means that some of our technology doesn't work, like an amplifier. So what do we do? Well, don't worry about it. We figured some of these things out so far, or we're working on it at least. So we have quantum repeaters and quantum memories, and these devices, while still in the R&D stage, they haven't been commercially available. They're not commercially available right now, but eventually, right? We're hoping that that would form the quantum network. So it'd be a repeater, it'd be your memory station, right? So you would get the signal to that location, and then it would be what's called amplified using nonlinear optics, usually. Um, and that way you're preserving the quantum information and you're not breaking the laws and you can actually amplify your quantum state, but doing it in a certain way. Or you
Hmm.
can store it until it's ready for you to send it again. However, these solutions, they require things like entanglement swapping. And so like we've mentioned entanglement, but we haven't really defined it yet for anybody. So maybe I should do that very
Yes.
quickly. So entanglement is this very bizarre property in quantum physics, right? Where you could have two particles and they could be separated by the size of the universe, right? One on one end of the universe, one on the other end. And if they are entangled, manipulating, measuring, doing something to one of those particles will instantaneously affect the properties of the other particle, which is just mind blowing because Einstein, right, has famously said there is a speed limit in the universe, and the speed limit is the speed of light. You can't go faster than the speed of light. And so now you have this phenomenon that looks to transmit information faster than the speed of light, which breaks all of our rules, all of our laws, right? It
Well,
doesn't
now
make
we're
any sense.
getting into the world of gravity, if I'm correct, because protons and things revolve around because of the, I guess, the nucleus or the cluster, whatever term you use. It's still gravity based. It's bound by a force to spin and to do the things that they do. And so I believe we're touching into the of like how space is expanding. It's through a property of gravity. And I think Interstellar touched on it. The film, very popular film Interstellar, the properties
Oh
of
yeah.
black holes, and so on and so forth. Correct me if I'm
Black
wrong,
holes
but
are
I think we're
crazy.
touching into that world of physics. Correct?
Sort of. When you think of an atom as a solar system, that was based on the Bohr model of the atom or the Rutherford model of the atom. Like when you think of a nuclear symbol, like that classic symbol with the spinning
Yeah.
circles,
Yeah.
right? But that's just a visual conception, right? We figured out that the electrons are not literally orbiting the nucleus because if they were, they would be losing energy because their direction is constantly changing. And so in physics, in classical physics, if your speed or your direction, if one of those properties is changing, you're accelerating, right? And so if I'm a vector, I've got a magnitude and I've got a direction, right? And if one of those is constantly changing, I'm an accelerating vector. And so if an electron was actually rotating around the nucleus, it would be constantly accelerating, and accelerating particles must emit radiation. So therefore, the electron would have to emit radiation, it would lose its energy, it would spiral into the nucleus, and the universe should not exist.
Okay.
And this was like a big, like, whoa, okay, our trying to apply classical ideas to our quantum world doesn't make any sense. And then that was the birth of quantum physics, where Erwin Schrödinger and several others came up with the wave model and the wave equation. And now it's this probability cloud and it's orbitals. And so the electrons exist in this like probability space outside of the nucleus. Yeah. But with entanglement, it's just like mind blowing that you could have two entities communicating with each other instantaneously.
Hmm.
Now, we can't yet use entanglement to do like a instantaneous communication. Why? Because in all of these properties, in all of these protocols, there's always a classical phone call that has to go along with it. So even if the superposition state between the two particles has collapsed and Alice has done the measurement and Bob has the answer or whatever, it's actually still random. And they need to have what's called a reconciliation. They have to have a phone
Hmm.
call. Alice and Bob have to make a public announcement, and it's part of the protocol. And so until they do that, even though they technically do have the collapsed states, it's not useful information yet. I know that was a big
No.
rabbit hole.
No, no, no. But I love your explanation.
Excellent, excellent. And so yeah, this picture here of someone bending the fiber,
However, yep.
that's exactly the type of loss I'm talking about, right? So obviously like this is like it's just a glass tube that the light is traveling
Hmm.
through, and then this spongy stuff on the outside is just rubber so you don't break the glass, right?
Hmm.
And so if you bend that too much, the glass can't keep the light in. It can't keep, it's too the angle is too harsh, and so the light will escape. And so even if you keep the light perfectly, the fiber perfectly straight, you're still going to get an average loss of zero point 0.3 dB per kilometer, and that's actually a lot.
Yes.
It's not bad for our classical systems, but for our quantum systems, that makes a significant change.
Hmm. And folks, just so you know, when she mentions not bad for classical systems, people are like, well, then classical systems are better in this regard. What she's referring to is there's a lot of collision with packets and how data is sent per how our classical computers are structured for sending data through a network, right? And so there are packets, there's reassembly, there's protocols that help with that interpretation, the transmission, transport, as well as reassembly and presenting it back to an application. So when it comes to packets of data, it's a little bit different, and there's several different ways to do error corrections and to compensate for certain things when it comes to that signal.
Exactly. And error correction, like you mentioned before, for qubits, is very important, right? So we're always dealing with errors, whether it's communication, sensing, computing. And so it's how do you mitigate those errors? How do you add So you could multiplex your channel, for example, like in our classical systems, right? You're using wave division multiplexing, for example, to send like multiple channels of information down one fiber. So you can do the same thing in quantum, and then by making that redundancy, you can use that to mitigate the loss. And so even if you lose, 8 out of 10 of your packets, your quantum packets, you still got enough that you can determine the signal. Yeah. And so yeah, so with quantum key distribution, like I said, it's guaranteed by quantum properties. So for example, quantum information can be transferred, but it can never be copied, right? And so that's the no cloning theorem. And then measurement disturbs the state or the system, right? So I imagine like a puddle of water, right? A pool of water. And if I was to slap the top of the water, I can see the ripples. I can see the effect of the measurement, right? So it's like
Hmm.
my hand was like the measurement and the water was the state, right? And so if an eavesdropper was trying to interfere with my photons, I will know because they will create errors and I'll be able to measure that. And then another very important one, single photons, and this actually comes into play with quantum random number generators, which is also a very
Hmm.
mature technology that's been around for 20 more years already. So single photons, they cannot be split in half, right? It's an indivisible bundle of energy, and it stores 1 qubit of information, or it could store more if it's a multiplexed state, right? If it's a qubit that has multiple frequencies in it or something. But the point is that you can't get half a qubit. So if an eavesdropper is trying to steal my photon, has to steal all the photon. Can't just take half the photon or a little bit of the photon, right?
Yeah.
And with quantum random numbers, if you send a single photon to a partially reflecting mirror called a beam splitter, and we can engineer these devices to be perfectly 50-50. So if there's a 50% chance the light will be transmitted through the mirror, and 50% chance it'll be reflected. And by doing that, you can have detectors on either side of the mirror, and sending in single photons one at a time, it has to choose. Do I transmit or do I reflect? And if everything is perfectly balanced, it'll be a perfect random number.
Wow.
You
And
just get the
folks, just to
zeros
kind
wrong.
of just highlight how wonderful she is just laying out the knowledge, and it's so easy to envision it as she's speaking. So, and this is some of the content that's in the training courses, correct? And
Yes, it
wow, this
is.
is just wonderful. Very simplistic way of laying out, and laying out really complex things that everybody can wrap their heads around. So kudos to you for creating such great slides, and just the way you present it. It's refreshing because a lot of folks can't really have a struggle with trying to present really complex ideas to the average person. And I think you're doing splendid.
Thank you so much. I really appreciate that. And I know exactly what you mean because I've been doing presentations now in academia for a very long time. And then I've transitioned to giving presentations to federal agencies like the CSA. And you have to speak in a different language, right?
Mhm.
It's not a room full of PhDs that all have been studying the same thing that you have for the last 20 years, right? And they're very intelligent people. And so you just need to speak in a language that they understand. And so you don't have to break out all the crazy math.
Yes.
But if you want me to break out all the crazy math, I got that. But yeah, I'll just finish on this slide. And so, like
Okay.
I said, we've got Alice, we've got Bob. A very common protocol is called BB84, named after the founders, Charles Bennett and Gilles Brizard. Gilles is still he's actually part of he's in Canada and he's part of our Canadian science team for the KeySat mission, or is advisor, part of this. And Charles was working with IBM at the time. And so this was a great union of the two minds, and they came up with a way that you could actually encode information and send it between these two parties using single photons. And in this case, it's polarization based. So it's like each one of these little arrows represents a little photon, and it has a different polarization orientation. And so we are literally making that encryption key using light. So yeah,
Wow.
I will stop sharing now.
Okay. Well, thank you for sharing some of the training slides and content. Again, just hearing you speak through it, it's very it's just refreshing because again, you really just lay it out in a super simplistic way. Not to demise the content you're delivering, but the way you're delivering is, I think, you could have a high school student and maybe even junior high to be like, okay, I got it. I'm getting to wrap my brain around it. So, and a lot of folks watching right now, I'm hoping that you got that same thing because that was a lot of information in just a few slides that she showed. And the executive course is like 1 hour chunks. The engineers get 2 hours. So imagine having 2 hours of content just like that. That's just simply
Mhm.
brilliant. And so,
Yeah.
and the folks who want to learn more about it, we're going to have the links so that you can sign up for those classes. They're live, they're given live, and you get, is it always you presenting, or is there a couple other
Yes, it
folks
is.
that present these courses as well?
Well, currently, it's me, and then
Okay.
if I get enough interest, I'll start getting some more quantum co-teachers.
Awesome.
Yeah.
So I like to segue now. We've thank you for so. I mean, we've went over an hour. I really appreciate you giving us this much time because you just have a wealth of knowledge, and thank you for sharing some of it. Because again, a lot of times, people get the surface level, but they can't really go down into the weeds. So thank you for thoroughly explaining everything so eloquently. But I'd like to segue now into some of my the questions I ask all my guests. And so one of
Yeah.
the first question that's my favorite to ask all my guests is you wasn't always a level 99, quantum PhD and an expert. There was a day one. And, we all start somewhere, right? And so what
Yep.
is your day one story when you made the decision that you was going to pursue technology, the sciences, engineering? What was your day one story?
Excellent question. I actually watched a movie called IQ with Walter Matthau and Meg Ryan. And Walter Matthau played Albert Einstein, and Meg Ryan was his niece, a mathematician. And so already I was hooked because it was a female mathematician doing, hard science and stuff like this. So I'm like,
Yeah.
this is cool. And I was only 14, and I heard these terms in the movie, quantum physics, physical chemistry, special relativity. And I'm like, that sounds cool. What's that? So I wrote them down. I went to my public library and I got to out some books on these topics. The librarian thought I was a little crazy, but took me to the right aisle and I was hooked. And I found educational material and a mentor at the University of Calgary that could explain these concepts to me, even though I hadn't taken formal like calculus. And so I was learning about like quantum mechanics and the fact that atoms could act like a wave and a particle. It's
Mhm.
like, I feel pretty solid. What are you talking about? I could be a wave. Like,
Yeah.
that's just mind blowing, right? And then I went on to take my bachelor's of science in physics and so on. But it was really that spark when I was a child, wanting to understand how things work at the fundamental level.
Hmm.
And I was always interested in astronomy. I was taking like astronomy classes as a like astronomy clubs, things like this. And so it's really interesting the union between quantum physics and astronomy, because like when you see the aurora borealis, the northern lights or the southern lights, you're actually watching quantum physics in action. And that's the atoms in our atmosphere getting
Hmm.
getting excited by the energy from the sun, the solar flares and the solar radiation, exciting those atoms. And atoms, each atom, each element has its own individual rainbow, right? Its own individual spectrum. And so you're seeing, the greens of oxygen and the purples of nitrogen and reds of hydrogen, all being excited in the atmosphere. And so that's quantum physics with your eyes.
Wow. And I love that you mentioned that, the film inspired you because it was a female mathematician played by Meg Ryan.
Mm.
You mentioned Einstein. And so Einstein, one of the all-time greatest mathematicians, Emmy Noether, he praised her as being one of the most brilliant minds. And every now and then I'll come across a mathematician. Like every time I do a presentation on quantum computing, I always ask the room within the first 2 minutes, is there any mathematicians in the room? So that way I know how hard I got to go with the math that's in my presentation. But
Yeah.
you mentioned that that you was in astronomy and study of space and so forth. How fitting is it that it's kind of almost like what do they call it, kismet or fate
Yeah.
that you would be working with the Canadian Space Agency. putting a
It is.
satellite next year into space and leveraging your engineering, your physics, and all your knowledge, and then now getting that opportunity to work with such a wonderful experiment like that. That has to be almost like what's the word I'm looking for besides fate, kismet? It's almost like a
Yeah.
full circle you've come from that, young person to where you are today, having that experience, if you will. Um, so
Yeah, I
thank you for
agree.
sharing your day one story. Along your
Yeah.
journey, and I know you have so much miles and miles more of a career to go. So it's not like the honorary Oscar where you're not making more movies. Obviously, you're going to be
Right.
so influential for years to come. But with that being
Thank you.
said, up to this point, obviously there might have been like instructors, professors, colleagues, managers, directors,
Mhm.
bosses, or even people in industry you admired. That this the I guess the goal of this question is: are there any names you want to shine a light on and just pay homage to say these people have had such a positive impact on me, whether there's someone you directly worked with or knew, or just someone in industry, like this person was like the poster child of science for me, and I wanted to be like them, and they had that positive influence on me.
Yeah, I mean, I was really lucky. I went to the University of Calgary and I got to meet a professor, Dr. David Fry. And like I said, I was only 14, 15, and he took time out of his schedule. And I know
Wow.
how incredibly busy professors are. It was unbelievable. And he helped me do experiments in the lab. I got to do a fourth year university experiment in the lab. Yeah, it was really really cool. So I definitely want to mention him. He's been a very strong mentor in my life. I also have had the privilege to interact with and meet Ray Laflamme. He wasn't my direct supervisor, but when I was at the University of Waterloo at IQC, he's one of the original founders. He recently passed away, unfortunately, but I got my chance to share some nice stories with him. And I just loved that no matter how recognized he became or how brilliant he is, he would talk with everyone. And I think that's something
I
that I
love
want
that.
to continue to do. Yes.
Wonderful.
Yeah. Because
Um,
there's a lot of people that get very snobbish as they get higher up in their degrees.
Yeah. But it's amazing how just a few minutes of your time and interacting with someone, you could completely change the trajectory of someone's life, for
That's
years to
right.
come, right? And,
That's right.
kindness is something that never goes out of style, and that we don't
Mhm.
have enough of in the world. And so I love to hear those stories, how just two people had such positive impacts on you. And here you are today, doing just tremendous work. Um, so we've done a lot of tech talk. Thank you for giving me an hour plus, and thank you for sharing your day one stories. Now I'd just like to go into what I call my rapid fire. This is purely for levity to just kind of have a break from the tech talk for a moment. These
Mhm.
are my rapid fire questions where there's no right or wrong answer. I'm just going to throw some questions at you. Whatever the first answer pops in your mind, just kind of blurt it out, and we'll have a laugh or two. So if
Mhm.
you humor me, I'll start off with the first one that will split every room of technical people. So Star Wars or Star Trek?
Oh, okay. I gotta say Star Wars because I made a lightsaber as my undergrad project for at the University of Calgary. I have a picture of it, but this is
Really?
rapid fire, so I shouldn't. Should I disrupt your rapid
No, well,
fire?
if you have it nearby, we'll take a pause in the
I
questions.
do, I do, I do. Hang on, hang on, hang
All
on.
right, folks, we're
I
gonna get
think
to
it's a
see.
cool picture.
Uh-oh,
So,
lightsaber,
yeah, it's this beam in the middle of the table
and it
here.
ends
Yeah, you can see that the light starts to dissipate at the end
dissipate.
here. And
Yeah.
so it went for almost a meter. It's called a Bessel beam. It's caused by a conical mirror that's hiding behind this big glowing cube over here.
Uh-huh.
So it's a cone-shaped mirror, and when the light reflects off of it, it interferes with itself, and so it creates a beam that's the same intensity and the same size for a set distance, and then it just refracts away.
Wow, look at that lightsaber, folks. So Star Wars right off the
Yeah.
bat on the rapid fire questions. So when you say Star Wars, which franchise or trilogy is your favorite?
Oh, the original. Are you kidding
The
me?
original, okay. And who's your favorite character?
Oh, Princess Leia.
Princess Leia, okay. All right, next question. Cake or pie?
Oh, um, I'm gonna go with pie.
Pie? What kind of pie?
Apple cinnamon pie.
Hot or cold apple cinnamon pie?
Ooh, warm with vanilla ice cream.
Okay, all right.
Yeah.
Is a hot dog a sandwich?
No?
Okay. What has been What has been your most favorite book of all time that you've read, and what was the last book you've read?
Oh, okay. My f- my favorite book of all time was probably like one of those mystery novels from like Mary Higgins Clark when I was a kid because
Okay, Mary
she
Clark,
would
yeah.
paint such a strong picture in my mind. Like I could literally like see the imagery and stuff like that. So,
Mhm.
but a more recent book would be a Jordan Peterson book. So
Oh, Jordan Peterson, I
12
love him.
yeah, me too. Yeah. So the 12 rules book, 12
Okay.
rules to live your life for I can't remember the exact title, but yeah.
Okay. Well, if you'll give me the link to his book, whether on Amazon or any site, I'll put it in the description below. So, folks, I want to always save you the Google search. Check out the links below. Speaking of links
Definitely.
below, if someone that's watching this right now says, "Hey, let's say they can't necessarily, afford the training that you have, even though it's super affordable. Anybody that's working in IT cyber, you should check it out. But let's say it's someone that's, in a career field that they're looking at transitioning into technology, and they're thinking, "Hey, I think I want quantum to be my entry into tech and cyber." Because you mentioned
Hmm.
earlier, like with the one company, you don't have to have necessarily a PhD to get into these fields. So let's say someone wants to approach learning quantum. And folks, I advise a lot of you to look at IBM Qiskit. They do have a
Hmm.
free programming courses and lots of documentation that's absolutely free. You can do simulations on there. I think that's a simulated quantum circuit, if I'm not mistaken. But they do
Hmm.
have a free program where you can get a lot of education. But do you have any sites or resources that you would recommend people to go check out?
Yes, yeah. So lots of the quantum computing companies also offer free services, tutorials, online training, even access to, 10 qubits so you can start learning how to program on a quantum computer. So I recommend looking up, like you said, Qiskit. Also, Xanadu is a quantum company in
Yep.
Canada that makes light computers with light with photons. They have Penny Lane is their software. Also, there's QED-C, so it's QED-C. I'll give
Yes.
you the website.
Mhm.
And so they're a great consortium that has resources online, even a jobs board if you want to get into the industry. Quantum Industry Canada is another one. So they are trying to bring a spotlight to all of the companies in Canada that are working in the quantum industry. And then I myself have a lot of free content online. So I'm on YouTube explaining these things, whether it's for my academic job or for my industry job. And Also, I have workshops with MyTax. So MyTax is a nonprofit organization that works with the federal government of Canada to deliver training. And so this is accessible to students through a university. So it's possible that you can access this free training if you're a registered student.
Wonderful. And all of
Yeah.
those things, Katanya will give me all those links and just pause the video, click down below, check out all the links down there because it's just so much info. It's just a wealth of information. I always tell people ingest all of the free stuff first, and then you'll have that foundation to go, okay, now I want to go and pay for this course and pay for that course. But first, I'll
Mhm.
always ingest what I call YouTube University and all the free things. Um,
Oh, and one
I,
more.
oh,
The Quantum Insider. The Quantum Insider. I use them a lot to keep up to date on information
And
in the
then,
industry.
folks, that's what I call being plugged in. If you're gonna,
Yeah.
go into this industry, you got to get plugged in. You got to have your news feeds, your sources. You
Yeah.
gotta, you got to read every day, right? You got to always be learning, keeping the brain sharp. I always call myself when people say, "Well, Jim, you're a multi-domain cyber expert." I'm like, yes, but I do 400 to 600 CPE continuing education hours a year to keep
Hmm.
myself as strong mentally as possible, knowledgeable as possible. And
Yeah.
I call myself a perpetual student. People use the term expert, but I'm like, I'm a perpetual student. I'm always going to be
Yeah.
learning. Just this past hour plus, I've learned so much from Catania, and I can only imagine taking a course. In fact, I probably will be taking a course, so I might do a follow-up
Love
review
it.
for that.
Love it.
Catania, a lot of us is super busy careers, super demanding with times. I know that you probably have, a busy schedule, for this next several months,
Mhm.
but a lot of us professionals, we do try to carve out time in our busy lives and schedules to make room for whether we give of our time, energy, or money to like nonprofits, charities, volunteer work, and causes that are near and dear to our heart. So what this question is are there any of these types of causes that you'd like to shine a light on? It doesn't have to be related to tech or quantum. It could just be something that, hey, this is something that means something to me, or this is an organization I want to acknowledge they're doing some great work in the world and making a difference in the world. That's what the question's for.
Yeah, I love that you're asking this question. Thank you. I actually am a volunteer with a charity called Space Place Planetarium Canada. They're a nonprofit organization that's trying to bring a planetarium back to Toronto. So
Okay.
Toronto
So
is
wait,
a
wait.
very
Toronto
nice.
does not have a planetarium?
Exactly. Toronto's
Come on.
one of the only major cities in the world to not have a planetarium.
Uh-huh.
Yeah, so the original one closed in 1995.
Okay.
And so I've been working with them actually for the last 6 years to get a planetarium. And I think now there's been a spot located, but we're always looking for more help, volunteers, and donations. So I will also give that link to you later. And I myself, I contribute with online blogs. So I've written blogs about the KeySat mission
Mhm.
because that's a nice combination of space with
Yes.
quantum. I've also given online talks. So there's a YouTube talk explaining the quantum industry and the links between quantum physics and space. And so you can find that online.
Wow. And all of those links and more will be in the description below. But the fact that planetarium does so much for our youth and for
Mhm.
adults too. I mean, anytime you ingest new information, and especially visually, it just opens new pathways. It creates, the neurons in our brains gets to make more pathways. It gets to grow and opens up. When I say it opens up your mind, that's what these places do. Museums, planetariums, and these things. We need them for current generations to future generations. So great kudos on the great work that you do, both in your demanding career as well as, giving of your free time and energy and money and everything that you do for the put the planetarium back in Toronto. So again, folks,
Thank
please
you.
support that. It's such a great cause and it has a generational impacts, right? It's things that we might not see immediately, but 10, 20 years when those kids have an experience with that and then they go on to pursue STEM careers and they become the future physicists, scientists, engineers that make the world go round even better in the future. It takes math, science, and technology. All these things have to come together to make our world a better place, to sustain our planet as well as explore new planets and so forth. So
Mm.
I just want to just thank you again and again and again for giving us so much of your time. We've ran so far over time, but it's just been it feels like it's passed by super fast, and that's just
I
because
can't believe it's been only that
but
much.
uh,
Yeah.
but what I like to do with all my guests is I give you the final word. So whatever you like to talk about, it doesn't have to be about quantum. It could be about whatever you'd like to talk about, but the final word is yours. And take us out.
Well, I just want to say thank you again, Jim, for having me. This has been a great experience. I'm new to the podcasting world, so I'm getting to learn all this with you. And yeah, I just want to encourage anyone watching, listening, that if you are interested in the quantum industry, what is a quantum computer? How could I get involved? Please reach out to myself on LinkedIn or through my website. Take a look at the NATE courses. I think you'll be really interested in the topics, and I've been curating the content as over the last 2 years. So this isn't just something that I thought people would want to know, and now I'm gonna like talk to you for 2 hours, and you're gonna be like, I'm not sure about that. No, like I've had my clients actually say, hey, can you teach me X, Y, and Z? And that's what I made. So I hope you join me in November
Awesome. So
or next
November's the
year.
next class. So thank
Yeah.
you again so much, folks. Katanya Kuntz has just given so much information and knowledge. Again, find her on YouTube, find her on socials, connect with her on LinkedIn. Again, just a tremendous professional, expert, PhD, all the accolades and titles. She deserves so much more. And she's got so much she's going to do for every industry. The research and experimentation she works on is going to just move our frontiers even further. So again, thank you so much for giving of your time.
Thank you again.
All right, have a great day.
You too.